So last time, we looked at an example. I wrote it down to remember exactly what it was because I want to pick up from there. It was the vector 2x minus 3x cubed. Thinking of this as a vector inside the vector space of P3, polynomials of degree up to 3, right? So this is an example of a polynomial that's cubic. And we said, well, in P3, there's a very natural basis. A very natural basis I'll call B, which is our basis, which is just the powers of x. X to the 0 or 1, x, x squared, and x cubed. And so what we can do is we can express this vector in terms of that basis and just read off the coefficients in terms of that basis. Right? Like it's already written to say it's 2 times the constant plus 1 copy of the next basis vector x plus 0 copies of the next basis vector x squared minus 3 copies of x cubed. And so we said we can just express this as the a coordinate vector that expresses the coordinates of this vector in terms of this basis. And it would just be 2, 1, 0, minus 3. And I just want to stress that this is now a vector that lives inside of R3. No, it doesn't. It lives inside of R4. This is a 4-dimensional vector field, and P3 is a 4-dimensional vector field over the ground field of R. And so when you express it with the coordinates is just going to live in R4. If this was the polynomial of complex coefficients, it would just live in C4, right? So that's not a problem. Whatever your ground field is, whatever your scalars are coming from, that's where this guy's going to live. But then we did last time, we continued and we said, well, there are other bases we could have chosen. So another basis, for example, that we could have chosen is the one that's 1 plus x plus x squared, 1 plus x squared plus x cubed. And in previous lectures, we verified that, in fact, that is a basis for P3. Any polynomial of degree up to 3 can be written as a linear combination of these guys. And we did that. We took this vector. We took the vector 2 plus x minus 3x cubed. And we figured out what it would be if you write it as a linear combination of these guys. And we read off the coefficients. And those coefficients came out to be, let's try to remember. Negative 3, 3. You need a negative 3 here in order to get this coefficient of this guy is going to be negative 3 in order to get you negative 3x cubed. But then it also gives you a negative 3x squared, which you cancel by making a 3 the coefficient of this guy. So then you get 3x squareds. And now you have negative 3x's and 3x's, so that's 0 x's. So you want 1 more x, so this should be a 1. But now you have negative 3 1s, and 1, 1. So you want this to be another 1. So your constants add up to 2. We did this last time. You can just solve the system of equations. What linear combinations of these guys give you this vector? And I'm pretty sure it came out to be this. Yeah? Okay. Great. Which is also a vector in R4. So perhaps the picture you should have in mind then is we're starting off in some vector space. In this particular example, this vector space is P3. And in that vector space, we have some vector v. And then what we're doing is we're moving from belonging inside that big vector space v to living inside of a copy of, well, for us, R4. So whatever your ground field is to the dimension of your vector space. And so we're sending, let me draw a different color here so it pops out. We're sending v to some coordinate vector here, right? And so we're turning v into whatever the corresponding coordinate vector is here. That was turning him right here into 2, 1, 0, negative 3. But then you might think, well, we did it again, but with a slightly different map. So we still sent it into Fn, but this time with respect to a different basis. So now you have some other vector v turned into some other basis c. So you can map it down to a copy of Fn, or you can map it down to a copy of Fn. You get different vectors. What we want to talk about today is, well, is there a way to move directly from one of these to another one? Right? How can I move from here to here? What's a map from Fn to Fn that changes my basis? So what we're trying to figure out is a map that will perform a change of basis for us, right? Okay. So maybe like this is a familiar story. How do we do a transformation from Fn to Fn? What's one way that's going to do that? Like from Rn to Rn. What's a map from Rn to Rn look like? One you talk about in linear algebra. A matrix, right? It's like a matrix, an n by n matrix is a map from Fn to Fn. Or Rn to Rn, more generally Fn to Fn, where your coefficients are just coming from whatever your field is. So can we think of a matrix that sends us from this vector to this vector, right? Well, there are lots of matrices, but more generally, is there a matrix that sends us from this vector with respect to b to some other vector with respect to c? That's what we're trying to figure out. So let's think a little bit more about what's going on here. And one way to think about what's going on here is let's start with this guy again and say that 2 plus that x minus that 3x squared in terms of c, we can think of as, well, in order to express this in terms of the basis c, it would be sufficient to figure out how to express 1 in terms of the basis c, how to express x in terms of the basis c, how to express x squared in terms of the basis c, and how to express x cubed in terms of the basis c, and then take a linear combination of those. 2 times the first one, plus 1 times the next one, plus 0 copies of this one, plus -3 copies of this last one. Well, you need to take a minute to convince yourself these really are the same thing. But think. If you express something in terms of your basis c, and you multiply that by 2, you should convince yourself that's really the same as moving the 2 inside, right? So take a second, think about how scaling works, and agree, okay, yeah, it's fine. And same with addition. That if you have some vector expressed in terms of the basis c, and some other vector in terms of the basis c, and you add them together, that's the same thing as adding 2 vectors then expressed in terms of the basis c. But I think that's pretty clear, since this is only going to come from just reading off the coefficients of linear combination. So when you scale, you're scaling those coefficients. When you add, you're just adding those coefficients. So that should be believable. But you can convince yourself of that. Then it's like, okay, so what do we get? And well, we could just calculate this. So if we want to just calculate this, you're like, it's 2 times, what is 1 in terms of that basis c? How do I 1 in terms of this basis? Well, it's right there as 1. So 1 copy of the first guy, and 0 copies of everything else, right? How do I write x in terms of this basis c? How do I write x in terms of that basis c? Yeah, you want a copy of this second guy, but then you have a +1 you need to get rid of, so you need -1 copies of the first guy. So if you take -1 copies of the first guy, you get a -1, 1 copy of the second guy, add those together, now you're left with just x. So -1 of the first one, 1 of the second, 0 of the rest. How do we express x squared with respect to this basis? Yeah, we want a copy of here, this guy, to get you x squared. but then you want to get rid of your 1 plus x, so you need to subtract off the second guy. So we're going to subtract off the second, add the third, and zeros for the rest. And finally, how do we get the x cubed? Well, same game as before. We want to copy the last one. Then we want to get rid of all this other pieces, x squared plus x plus 1, which just means we need to subtract off the penultimate piece. So we're going to do 0, 0, minus 1, 1. Yeah? OK. So it wasn't too bad to convert these guys into the basis C. But now the claim is if we just add together the linear combination of those, we should get the right thing. Let's verify this. 2 times the first number, 2 times 1 is 2, minus 1, so we're at 1. And so it's just 1, 0, 1, 0, 0, so it's a 1, 0, 0, doing the third row now, 0, positive 3, 0, 0, 0, negative 3. Which is, sure enough, exactly what we had before, right? So things agree, things are matching up. But what's more significant than actually the calculation is this process to figure it out. I mean, if you look at what this is saying, this is really the same thing as just taking the matrix that you get from combining all these columns. The first column, 1, 0, 0. The second column, negative 1, 1, 0, 0. The next column, 0, negative 1, 1, 0. And the last column, 0, 0, negative 1, 1. And multiplying that matrix by the vector, which is these coefficients, 2, 1, 0, negative 3. Because the way matrix multiplication works is when you do your row times column, you end up with 2 times all the guys in the first column, 1 times all the guys in the second column, 0 times all the guys in the third column, and negative 1 times all the ones in the last column, and then you sum together those columns, right? So that matrix multiplication is exactly this expression here. Right, so it's a little reminder of how matrix multiplication works. Be happy with that? That's good? Yeah?
The negative 1 is supposed to be a negative.
That negative 1 should be a negative 3. That's exactly right. That's exactly right. That negative 3. Good catch. But more than just this particular example, we're now seeing the pattern emerge. Like, what is this thing really? This thing really is just the first column is what we got when we converted 1 into the basis C. The second column is what we got when we converted the next element of the basis B, x, into the basis C. The next column is just what came from the x squared converted to the basis C. So the x squared being converted into the basis C. And the last column is what happened when we converted the x cubed, the last element of our basis B, into the basis C. And then what is this vector? It's the coordinate vector from taking our vector here and converting it into what basis? B. And when we did that, we ended up with this guy, which is that same vector v, but now with coefficients in C. Right? So how do we convert from coefficients in B to coefficients in C? We multiply by a matrix where each column was just the elements of the basis B converted into C. So let's write this down as a result and show that it works in general. So here's my theorem. So we should be given some vector space that has multiple bases. So let's say one basis is B and another basis is C. then the claim is for any vector you pick inside that vector space, if you want to convert that vector from having coefficients in B to having coefficients in C, if you want to find the coefficient vector in terms of C, given the coefficient vector in terms of the basis B, you need to multiply by some matrix that does the work of converting B into C, where that matrix is just going to come out to equal, is defined to be the matrix you get from, oh, well, I should give these guys some names. Let's say that B is the basis comprising the vectors u1 through un, where n is whatever the dimension of my vector space is. Note, this is only going to work if this is finite dimensional, so I'm assuming this is a finite dimensional vector space, right? This has some dimension n. Let me just write that here. I'm assuming the dimension of my vector space is finite. And then C should be some other basis with some vectors. Let's call them maybe W1 through Wn. We showed last time that any two bases will have the same number of elements. That number of elements is your dimension, right? Okay. So then how do we convert from B to C? You just take all the vectors in the basis for B, u1 through un, and you convert those into C. I'll say a couple things about this matrix. First of all, this matrix is invertible. So the determinant is going to be non-zero. And what will the inverse be? What do you think the inverse should be of the matrix that turns vectors with coefficients in B into coefficient vectors with the coefficients in C? What would that inverse be? Yeah, it's just going to be the change of basis vector that goes the other way from C to B. And second claim, P of B to C is unique. That is, it is the only matrix that does this. There's no other matrix you can put here that will convert it for all vectors in your vector space V. So we have three things to prove. First of all, that this matrix actually does what we want it to. Second, it's invertible. Third, it's unique, right? Okay. First one's going to be the most interesting. It's pretty straightforward. The last two, they're going to follow very quickly. So let's prove this. I want to leave this picture here for now, so I'm going to clear this board. We're essentially going to do what we just did, but instead of working with a specific example, we're just going to work in general. So here's my proof. I just need to show that this really is equal to this guy. So let's just show that. Just let V be something in your vector space. Then we can write V as a linear combination of either one of our bases, either one. For now, it's going to be convenient to write V as some linear combination of your basis B. So it's some coefficient C1 times U1 plus C2 times U2 up through Cn times Un. Thus, Let's just show that this calculation works. What is my matrix times V converted into the basis B? Well, that's going to be the same as my matrix given by U1 through UN, coefficient vectors in terms of the basis B as its columns, times this vector, which is the coefficient vector for V in terms of the basis B. And what is that coefficient vector? Well, it's just these coefficients, C1, C2, down through Cn. These are columns. These are columns. So how does matrix multiplication work? Row times column, or equivalently, what ends up happening is it's C1 times all of your first things, plus C2 times all your second values, all the way down to the end. And so you end up with C1 copies of U1's coefficient vector in terms of the basis B, up through Cn copies of the basis vector UN's coefficient vector, whose coefficients are in terms of the basis B.
Well,
Yeah.
shouldn't it be in terms of basis C?
Oh my goodness, thank you. This coefficient vector, these should be in terms of C. That's our definition right here, right, in terms of C. Yeah, what you're about to see, right? Like, that's what we need. These should be C. Thank you, thank you, thank you. Good catch. So what is this? Well, as we said before, it's like, what is the coefficient vector scaled by C1? Well, that's just the coefficient vector of U1 scaled by C1, right? That's just the coefficient vector of doing C1 times U1. All the way through. So this is just going to be Cn copies of this coefficient vector is the coefficient vector of Cn copies of Un. And then the coefficient, the sum of the coefficient vectors of two vectors is equal to the coefficient vector of the sum. That is, this just comes out to be C1 U1 through Cn Un. Happy? Well, I mean, what is that? C1 U1 through Cn Un is just V. So that's just V in terms of C. So now we've checked that, yeah, this does what it's supposed to do. And we built it to do it, but now we verified it works in general. So we verified this first part, that this matrix does the trick. Okay, let's try and prove the second part, that the matrix is invertible. To do that, I'll just notice what is P B to C times P C to B times some vector whose coefficient, this is the coefficient vector with coefficients in C. Let's evaluate what this comes out to be. Well, we're going to do first the multiply by the matrix on the left. And by our theorem, okay, so I mean, I proved this theorem going this way, but you can just rewrite, you can rename C and B, and you have the exact same theorem for C to B, right? You have the exact same theorem. So now that we've proven the first part, we know that this first guy is just changing us from C to B. Or if this was a B, it would change us from B to C. So this guy, this first multiplication step is just going to give us a vector coefficient, the coefficient vector of V in terms of B, right? That's what it does, it changes it from C to B. And then this guy is just going to change you back. And so he's going to end up with this guy. And that's for all V's in your vector space. Hence, it's for all coefficient vectors. Hence, your multiplication of these two matrices must just be the identity matrix, the n by n identity matrix. But that means one is the inverse of the other. Thus, the inverse of one is just the other. So this pretty much comes for free. Like, this is rather immediate. Once you know what these matrices do, it's pretty clear that they're inverses of each other. The last point you might worry about a little bit more is, like, how could we possibly show uniqueness, right? Like, how do we know there's not some other matrix that maybe does the same trick? So, any thoughts on how to show uniqueness?
Assume there are two different ones and show the same.
Yeah, essentially. In this case, we're just going to say you have some matrix that does this, and then we're going to show secretly it's this matrix, right? So for uniqueness, you just need to suppose you have some matrix M that when you multiply it by the coefficient vector of V in terms of the basis B, you get the coefficient vector of V in terms of the basis C. For all vectors in your vector space. There'd be lots of matrices that might do it for one or two vectors in there, right? But let's think this is one that does it for all vectors. Okay, what should we do now? Well, it works for all the vectors. Let's pick some special ones. What are some special vectors we might pick? No, you'll just get the matrix times the zero vector is 0. Not very interesting. Basis vectors. Since this is true for all V in particular, it would be true for, say, your first basis vector of B. Right? That is going to come out to be your first basis vector in terms of the coefficient vector for U1 in terms of the basis C. But what is U1's coefficient vector with respect to B? Right. U1 is just equal to 1 copy of U1 plus 0 copies of everything else. So this is really just M times 1, 0, 0, 0, 0, 0 all the way down. Right? So what is this really? What is a matrix times 1, 0, 0, 0, 0, 1? A matrix times 1, 0, 0, 0, 0, 0 is all the way down. What does that give you? Just the first column, right? You're multiplying the entries in the first column by 1, everything else by 0, and add them together. You're just recovering the first column. This is just going to be the first column of M. Hence, we have the first column of M must be just the coefficient vector in terms of the basis C for U1. Exactly like we showed here, it should be. And of course, there's nothing special about U1. You could do the same argument for U2. You get the second column, or U3, or in general for any UI, right? And so on, right? It's true for all UIs. Good? So in our picture, we can fill it in a little bit, and we can say to go from the coefficient vector in terms of the basis B for the vector V to the coefficient vector in terms of the basis C for the vector V, you're multiplying by this special matrix that is going to be denoted P sub B to C. And to go the other way, You're multiplying by the inverse of that matrix, which is just the change of basis matrix from C to B. Okay, so this should be like, it's a little more abstract, but very similar to what you've seen in Introduction to Linear Algebra, right? In your first course in linear algebra, it's like, how do you figure out the matrix of some transformation? Well, you just ask, what does the transformation do to your basis vectors, like 1, 0, 0, 0, and then 0, 1, 0, 0, and 0, 0, 1, 0. You know, you just look at those elementary vectors, the basis vectors, and you just ask, what does the transformation do to those? And then you recover the matrix. So we're saying the exact same thing here. So to figure out this change of basis matrix, we just figure out how the change of basis works on the basis vectors, and you recover the matrix. This notation might seem a little bit strange, like why are we writing B to C with an arrow like this? It's like, seems like it's going backwards. But when you start thinking about compositions of things, well, I think it's a little bit helpful. So maybe you have some third basis D. And so that would give you another map that sends V down to the vectors V's coefficient matrix in terms of some basis D. And then you could be passing between like C and D. So there will be maps between these, which are just the maps that convert. It's just the change of basis matrix going from C to D, and the change of basis matrix going from D to C, which is, of course, the inverse of the guy above it. But then it's like, OK, what if I want to know what is the change of basis matrix to go from B all the way to D? Like, what is that guy going to be? What is the change of basis matrix to go from B all the way to D? So this is no mystery. You can just tell me. How do I figure out what this matrix is? Well, how can I go from here all the way there? Yeah, you do like one step at a time, right? So to go from B all the way to D, first I want to go from B into C, and then I want to go from C into D, right? If I wrote the arrows the other direction, you know, maybe you wouldn't see as well. It's like C to D, B to C. It wouldn't look as clean. But when you write them this way, it's like, well, now it's clear this is going from B, stopping along at C, headed to D, right? So maybe this justifies the notation a little bit. Because if you have any vector expressed in terms of a coefficient vector of coefficients in B, this changes it to that vector of coefficient vectors in C, and this changes it in terms of the coefficient vectors in terms of D. And then since we know that there's only one matrix that does that, the matrix is unique, we have, therefore, this matrix, since it does the same thing, must equally be the same as the multiple of those two matrices. So we're taking advantage of the uniqueness from the theorem to say, yeah, he must actually equal that product, since the product accomplishes the same thing that he accomplishes. That is, let me just write this down like as a little property. Well, I guess the property is right here. We have this composition. But in general, this is going to be really useful to, well, let me give you an example. Let me give you an example. Do we want to stick with this first guy? With these coefficients? I mean, we can. So here we had P3, and we had some basis, you know, like say the basis C, which was some ugly basis, was the basis 1 plus x, 1 plus x squared, 1 plus x squared plus x cubed. Ugly basis. What's another ugly basis? You want to make one up? Yeah, let's just make up something and, we'll squint our eyes at it, convince ourselves it's a basis, and if you want to go home and check it's a basis, you can. Maybe instead of a 1, we can put like a 2. It scales, so that's fine, right? We want something in the second rule that eventually give us an x. 1 minus x. Let's just be chaotic. That's great. And then we maybe make this 1 plus x squared, and then maybe here we'll have something like x plus 2x cubes. Okay, so usually convince yourself this is really a basis. Maybe it doesn't look like a basis, but the way to convince yourself is that you can get all of these standard guys, 1, x squared, and x cubed, from these guys. And you can scale this by a half, you get 1. Once you have 1, you can subtract it from this guy, you get negative x, scale it by a negative 1, you get x. You have 1, so you can take away 1 from this to get x squared. You had an x we got from before, so take it away from here, and then you can scale it by a half, right? So you can recover these standard bases from this guy. Okay. So let's say I wanted you to calculate the change of basis formula to go from C to D. So one way to do this is you want to take each of these guys in C and express them in terms of the coefficients of guys in D. So you want to take the first guy 1 and express that in terms of the basis D. You want to take the second guy 1 plus x, express that in terms of D. Take the next one, 1 plus x squared, express that in terms of D, and then take the last one, 1 plus x squared plus x cubed, and express that in terms of D. Now you can do this, but it sucks, right? The first one's not so bad, right? This first column, what's the first column? What is 1 expressed in the second basis? Yeah, half of this and zeros of everything else. So you can do it. You can do it. I actually don't think it'd be too terrible, but you can imagine in general going from some ugly basis to another one. This could be quite a tedious path. You would have 4 systems of equations you have to solve, right? Which is kind of gross. Solving each of these is a linear combination of these other ones. So what can we do instead? Well, this reminds us that instead we could think of this as a multiplication of C into something else, and then that other thing into D. So it's what should that something else be? Is there something else that's nicer for us to work with? Yeah, and it's this B is quite nice for us to work with. Although, typically, for the standard basis, it's known as E, so I'm just going to make a quick change and call this E, just to stress it's a standard basis. It's the one that's nice to work with, okay? I'm going to call it E, standard basis with just 1 x squared, x cubed. So pass in the middle first through E. And let's just see how nice this is. So let's check out this guy, P, E, C. It's saying express, how do we solve this? We're going to take each of the vectors of C and express them in terms of the standard basis E, right? So what is this first guy in terms of the standard basis E? Well, it's just this first guy again. 1, the first guy, nothing else. But how about him? What is he? Yeah, 1, 1, 0, 0. And how about him? Yeah, it's just the sum of the first 3. And this guy, Just the sum of the first 4. Nice. So like this one was super easy for us to determine. How about this guy? How about P, E to D? You're like, well, now it's a little bit harder. Because now we're trying to take the elements, the vectors that form the standard basis, and convert them into this difficult basis. And that's a little bit harder. It's like, it's much nicer to go the other direction, right? But we can go the other direction, because this is just going to be the inverse of going the other direction. So let's just figure out how you convert D into the standard basis, and then we'll take the inverse of that guy. So we've got D. So the first guy is 2, which is just 2 times the first element of your standard basis. The next one was 1 minus x. So that's just 1 minus 1, 0, 0. The next one is 1 plus x squared. So that's just 1, 0, 1, 0. And then it's x plus 2x cubed. So 0 copies of 1, 1 copy of x, 0 copies of x squared, and 2 copies of x cubed. And then we need to find the inverse of that matrix. Now in practice, maybe it's a pain to find inverse of matrices, but like this is a very easy thing to program, right? So maybe right now someone should like pull up some, little calculator tool or website and find the inverse of that matrix. But while you do that, I'm just stressing to calculate this, like really the process that's really easy to follow is instead in practice you're going to be calculating this guy. You're going to just think, how do I change things into my standard basis? Because if I know how to change things into my standard basis, then I can change between any 2 bases, right? Okay. But let's say, do your calculator, because we're going to check this result in a second. But let's say like you don't have any technology. Given the rate the world is going, you can imagine some apocalyptic event, I don't know, nuclear warfare or whatever, or alien visitation that wipes out all technology. This isn't inconceivable at this point. So if you don't have technology, and like the fate of the world depends upon you moving between 2 bases, so you really need to calculate an inverse of a 4x4 matrix, very plausible situation. How do you do it? Well, there's some long formula that involves going across some row and expanding and finding like minors. And you remember some of this, doing this by hand? That's a pain. What's the better way to do it? The better way to do it is like this inverse exists. You know it's going to work. What you can do is you make an augmented matrix. Have you seen this before? You make the augmented matrix where you put the matrix you want to invert right here. And then we're just going to draw a line to separate that. And then here we're going to put the identity matrix. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And now what we're going to do is we're going to use row reduction. Do you remember some of this from your first course in algebra? We're going to row reduce this guy on the left, keeping track of the changes on the right. And in the end, he'll be the identity, and he'll be the inverse. Right? So the procedure is you begin with some matrix M. On the right, you put identity. You do row reduction. You row reduce it until you end up with identity on the left, and you'll have the inverse matrix on the right. And so it's worth going back and remembering how this row reduction works and convince yourself that really is what you end up with. But in practice, just remember how this works. It's like, maybe 1's all the way here. We can add rows to other rows, and we can multiply by scalars, right? So it's like, OK, I want to get all these things to be 0. So maybe I should add a copy of the second row to the top row. So if I add a copy of the second row to the top row, he's now 2. He becomes 0. Add 0, so he's still 1. Add 1, and he's now 1. And add a copy of the second row to the top row. And very good. I add a copy of the 1 right here, so he's also 1. And so in the second row is still something like this. And then I still have my third row. And I still have my last row. Okay, since we're recording this on video, I'm not going to keep redrawing the matrix. We're just going to do it together. What do we do now? How do I get rid of this 1? Subtract a copy of the third row, right? So I subtract a copy of the third row. I'm subtracting 0, doesn't change anything. He becomes 0, he's still good. But I'm subtracting that 1, so this becomes -1. Okay, what do I need to do next? Well, I want to get rid of these 1s. Let's first make this into a 1 so we can clear them out. So I'm going to multiply the bottom row by 1/2. Now I'm going to subtract the bottom row from the top row. So that becomes 0. These are all zeros, but subtracting that 1/2 makes that -1/2. I'm going to subtract the bottom row from the second row. So that's 0. And subtracting 1/2 gives me a -1/2. And now I can multiply the top row by 1/2 to scale that down to 1. So this becomes a 1/2. This becomes a 1/2. This becomes a -1/2. And this becomes a -1/4. And I'll scale the second row by -1 to make this him. So what is the inverse of that matrix? The inverse of the matrix is just the guy on the right. It's 1/2, 1/2, -1/2, -1/4, 0, -1, 0, +1/2, 0, 0, 1, 0, 0, 0, 0, 1/2. And the claim is, if you multiply this matrix by this matrix, you recover the change of basis matrix. We can check it really fast, but let's just multiply the first row by the first column. What do we get? First row by first column, we get a 1/2. And if you multiply the second, third, or fourth row by the first column, you get all zeros, which agrees with what we said the first column should be, right? You can continue to multiply this out if you want to. I feel this like obsessive need to do it really fast. So multiplying out the second one, we get 1. The next guy gives us -1/2. The next one gives us +1/4. Going down to the second row now, I'm getting -1, -1. Help me out if I make a mistake. -1/2. Going down to the third row, we have 0, 0, 1, 0, 0, 1, 1. Going down to the last row, we have 0, 0, 0, 1/2. Very likely there's a mistake in there, but you can do the multiplication yourself and verify. But there you go. Maybe it would have been quicker to do the system of equations, but here's a general procedure. And these things are very computationally inexpensive to find matrices and their inverses. So in practice, you could program a computer to do something like this very easily. We'll stop there for today.